And now we talk about power flow in a DC machine. Motor, you mean? No, machine. It could be a generator, and sometimes it will be a generator. Electric power? No, power in general. You see, we talk of electric power on the electric part of the machine and of mechanical power on the axle of the machine. In a DC motor, the power flows like this. And there is the armature circuit of a very simple DC motor, an independently excited DC motor, the external battery, VT, and the current in the armature, and this induced voltage source, E sub A, the armature total resistance, including the contact resistance of the brushes with the commutator. How it all begins. The input power is, of course, Vt times Ia. That is the power that goes into the motor. Out of that power, immediately we have to subtract the losses in the armature's resistance, Ria squared. And what remains of that hits this induced voltage source in our equivalent model. That power is Ea times Ia. And you know what happens to that power? That power will be converted into mechanical power. That is the portal. This source is the portal between the electric world and the magnetic field. And that power goes into the magnetic field. And on the other side of that magnetic field, that becomes induced torque multiplied by the mechanical angular velocity in radians per second. Yes, not in RPM yet, radians per second. Who is the induced torque? Is that the torque that the user of the motor experiences? No, we still have to subtract frictions and other losses before we get to the output. But for now, that is also the P converted. The electric side of that converted power, Ea and Ia, and the mechanical one, induced torque, times the angular velocity in radians per second. Out of that, we subtract more losses. The core losses and the rotational losses, windage, friction and all that, and the stray losses. And what remains, that is what comes out of the motor as output mechanical power. This one, the output useful torque multiplied by the angular mechanical velocity of the motor in radians per second, not RPM. This formula is in radians per second. And such is the power flow in a DC motor. Please focus here on the P converted, the portal between the electric world and the magnetic field, and the magnetic field will distribute that power like so. In a generator, the power flow begins from the mechanical side. On the axle of that generator, we apply mechanical power, and that power eventually reaches this portal and is sent into the electric world's load, this box on the left of the diagram. Let's begin. The input power is mechanical power, is the torque of the turbine, the water wheel, whatever is moving our generator, multiplied by the mechanical velocity, angular velocity in radians per second. Out of that input power, of course, we subtract the stray losses, rotational losses, the core losses, and we hit the magnetic field. That magnetic field's power will be the induced torque, and that is slightly less than the input torque because of friction and all the losses, multiplied by the mechanical angular velocity in radians per second. That is a P converted on the mechanical side. That power will appear in the electric circuit over here in this E sub A source. And that value will be, of course, EAIA. Once that power is on the electric side of the generator, then it keeps flowing through RA and out into the electric load. We have to discount the losses, RAIA squared. And then we have the output power, that is VTIA. Such is the power flow in a DC generator. Thank you very much.